So here are three fractions, and what I'm going to do is I'm going to convert them into decimals. So 1/5, 1 divided by 5, using short division. 5s into 1 go 0 with 1 remainder. Bring in a 0 and a decimal point. 5s into 10 go 2 with 0 remainder. So 1/5 is 0.2, and we would refer to that as a terminating decimal. Okay? Now, 1/3, if I do 1 divided by 3, 3s into 1 goes 0, remainder 1. So we bring in a 0. 3s into 10 go 3. 3 3s are 9, so there's 1 remainder. Bring in a 0. 3s into 10 go 3, remainder 1. Bring in a 0. 3s into 10 go 3, with 1 remainder. Bring in a 0. And you can see what's going to happen. This is going to continue indefinitely. Okay? And so 1/3 is 0.333333333333 forever and ever and ever. And we refer to this as a recurring decimal. Okay, so this is a recurring decimal. Now, in order to identify a recurring decimal, rather than just using these three points here, so these the 3 points, because that could be misinterpreted. Sometimes when I write down an answer for my calculator, decimal answer, I might just put in 0.2783 ... and that doesn't mean that it just keeps repeating. So there is some notation that you can utilize to represent this. Now the one that I use is 0.3, and you put a dot over the value that is recurring. So this represents 0.3 recurring. Alternatively, you might also see this notation around where there is a horizontal line over the top of it, and that could be used as well. Okay, both these two things mean the same. You might want to double check your exam board for which one is more often used. I think you're probably going to see this much more than you'll see that. Okay, so it's nice to be aware of both of them, but I'd probably suggest running with this one. Now I'm going to take a look at another example here, 1/7. Okay, so 1 divided by 7. Now 7s into 1 go 0 with remainder 1. Bring in a decimal point as 0. 7s into 10 go once with 3 remainder. Bring in a 0. 7s into 30, well 4 7s are 28, so 4 times with remainder 2. Bring in a 0. 7s into 20 go twice, 2 7s are 14, with 6 remainder. Bring in a 0. 7s into 60, well 8 7s are 56, so 8, and so 4 remainder. Bring in a 0. 7s into 40 go 5. 5 7s are 35, so remainder 5. 7s into 50, 7 7s are 49, so that will go 7, with 1 remainder. Now, the moment that we get back to a 1 remainder, we're going to bring in that 0. 7s into 10 goes once. And we're going to get this exact same pattern again, because the 3 will be the remainder. Bring in another 0, then we'll get 4. 2 will be the remainder, then 6, then 4, then 5. We're going to get exactly the same values again. We're going to go 1, 4, 2, 8, 5, 7, 1, 4, 2, 8, 5, 7, 1, 4, 2, 8, 5, 7. Forever and ever and ever. It's going to repeat that pattern. So 1/7 can be written as 0.142857, and I want some way of identifying that it is just that piece that's going to be repeating. And the way to do that using this notation is to put a point over the first number that's repeating and a point over the last number. So that means that it is that stretch of values that are going to repeat indefinitely over and over and over and over again. This notation would write a horizontal line over those 6 values. Okay? But again, I would try and stick with using that notation. So this is how we can identify recurring decimals and what we mean by recurring decimals. They come in different forms. They don't have to be the same value, just repeated over again. So it doesn't have to be 0.9 recurring or 0.8 recurring. We could also have 0.128 recurring. Okay, so what that means is it goes 0.1288888888 forever and ever and ever. Okay, so you can have some non-repeating e bits at the beginning, and then it starts repeating. Okay, so you can have a string of values like that, or you can have just one digit, or it could be 0.121212121212 forever and ever and ever. So these are recurring decimals, and we're going to be exploring how we can convert from recurring decimals back into fractions in this section, as well as working with recurring decimals in problems.